You know, one thing we've talked about, Mr. Sams, is that there's energy in everything.
Yes, this is true.
Energy. And I'm not just talking about energy when we, like, burn something, but there's energy when you have a phase change.
All right. What do you mean by phase change?
There's several varieties of phase changes. It can go from a solid to a liquid, or a liquid to a gas, or a gas to a liquid, or a solid to a gas. A phase change from one state to another state. And I'm not talking Colorado to Texas.
They don't touch anyhow.
Yeah, I know. Well, you know. You see, folks, we're talking about phase changes. What happens in a phase change from an energetic perspective? And so the focus of this will be a video that we're going to watch about, well, we're going to heat some water. Kind of boring, but actually it teaches us some interesting things. Okay, so let's do that. Let's talk about a couple of interesting terms, some definitions. So we'll copy these down. What is the molar heat of fusion? Well, it's the energy required to melt 1 mole of a substance.
Okay.
So melt means, what does that mean?
Melting, we're going from solid to a liquid.
So if I'm going from a solid to a liquid, it requires a particular amount of energy.
Yeah, now this one's always struck me as weird. Why it's called fusion, but you're going from a solid to a liquid.
Why does that struck you as weird?
Well, if you fuse something together, you stick them together. It seems like it should go from liquid to solid.
I wish they called it the heat of melting.
Exactly.
But they didn't.
But somebody didn't.
Now this would be an endothermic reaction, because
yes.
if you think about it, to melt the solid, the
you have
ice,
to put energy
maybe, for
into
example,
it.
you have to put energy into it.
Right.
So it's the energy. Now, something important to happen or to say about this is, as the energy is being added, the energy is being used to break. We'll call them the bonds. Typically, it could not necessarily, it may not be bonds, it might be what we call intermolecular forces, which we'll learn about in a later unit. It's being used to break the bonds, and a very weird thing happens. Oh, by the way, the unit for that, or the symbol, is delta H FUS.
FUS, for fusion.
For fusion. And the value for water, the one everyone talks about, is 6.01 kilojoules per mole.
All right, and you're going to use that number, so you might want to jot it down somewhere.
Yeah, a little table or something like that. Okay. All right, there's also something called the molar heat of solidification.
Now this one makes sense. This is the energy associated
Solid.
with changing 1 mole from a liquid to a solid.
So it's the opposite of what we're
To
talking
freeze
about.
it, right.
Now this is a weird one, though, actually, if you think about it. So if I go from a liquid to a solid, then it's actually exothermic.
Exothermic, right. For the liquid to freeze, it has to get rid of its energy.
Right.
So it's got to go away. That's why we put things in the freezer. The freezer doesn't make things cold, it makes them less hot. So it takes the energy away from things to freeze
Exactly right. So there's a lot of confusion about that. It's called delta H solid. And actually, you know, the answer for water, interesting, is the same
It's
number.
the same, but the sign
but the
is different.
sign is different.
Right.
Well, it's because it's exothermic.
Right,
so the
so that's
heat
why
of
it's a negative.
solidification and the heat of fusion are going to be the same value for a given substance, except the signs will be reversed. Okay? Interesting question, Mr. Sam.
Yep.
I know what the temperature of that water is without sticking a thermometer in there.
Stupidly cold.
Stupidly cold. So these people are swimming in an ice field.
Yes.
So you know what the temperature is?
Cold.
How about 0 degrees Celsius?
How do you know it's 0 degrees
Well, because
Celsius?
what's happening is we've got solid ice, and it's turning into liquid ice. And I have this double arrow thing going on, where the arrows, some of it's melting and some of it's freezing.
Okay.
And I know the freezing point of water is 0 degrees Celsius. The melting point of water is 0 degrees Celsius.
So if that phase change is happening, it has to happen at 0 degrees Celsius.
So those people are in 0 degrees Celsius water, which of course is 32 Fahrenheit.
And stupidly
cold. All right. I think to help us truly understand this whole concept we're trying to get across is we should watch a short video. Well, I'm not sure it's that short, but watch a video clip of water as it warms up.
Okay.
Hey, Mr. Sands, what you got there?
I got a beaker full of ice and water.
Yeah, I see that. Yeah.
Our ice is melting.
Uh-huh.
So the temperature's right around, pretty close to 0.
Yeah, pretty close. I can see that.
Okay, so you'll notice that as this melts, the temperature's
Staying about the same.
You know, I'm going to put it on the hot plate here.
Oh, it should get hot really fast now.
No, it's actually still going to stay right around where it is.
Why?
Because when things undergo a phase change, the temperature does not change.
Yeah, that's right. Actually, folks, what's happening is the temperature does not change because the energy that is being added to it is being used to break the chemical bonds, not to that holds the ice together, not to heat up the water.
Right.
So it's staying pretty close to 0. You can kind of see that going there. Yeah.
All right, so we're just going to let this go for a while. We'll come back when it's done melting.
Okay. All right.
All right, so we're really close here. Almost all my ice is melted, so we got a little bit of an increase, and that's...
Yeah, because it's hard. The thermometer has a hard time measuring. So it's all the energy is being used to melt that ice, and there's
Right,
hardly
and
any
now
ice left.
all my ice is gone. So we should see a pretty steep increase in the temperature of this water now that all the ice
Yeah, I
is
can
gone.
see that line. It's going up and up
That's
and up,
going
isn't
up
it?
a
Look at that there,
lot faster than it
right
was
there,
when it was
folks.
undergoing its phase change.
Going straight up. So right here, typically we consider it flat right here, and it's close enough to being flat, but the temperature is just rising and rising and rising
Yeah, it's going
as
up
the
really
energy
fast.
here source from the hot. Ooh, that's hot. That hot plate is causing it to rise. Yeah, so it's going way up quite fast. Now something interesting is going to happen though when we reach the boiling point, but we'll wait and see what happens there.
Yep.
So why don't we pause the video and we'll come back here in a few minutes. What do you think? Well, Mr. Sams, here we are again. It looks like you're continuing to stir that. We're in about 6 minutes, 7 minutes, something like that.
Yep.
And it looks like the temperature is continuing to rise. So
is.
the energy that's in the that's coming from the hot plate is being used to raise the temperature of the water up a number of degrees. And so right now we're up to, looks like 64 degrees.
Yep.
And so we're going to pause the video and we'll come back when we get close to the boiling point of water. All right, Mr. Sams, we are approaching the boiling point of water right here.
Yes, we are.
In fact, I can kind of see. It looks like it's boiling.
Yeah, I got little bubbles going there. That could just be some dissolved gas.
So the
that's in there.
temperature can probably just it'll just keep going up, right?
Well, it'll go up until we actually start to boil and it starts to undergo a phase change. And now, during the phase change, no matter how much energy you put into it, it doesn't change the temperature of the liquid.
Because the energy, folks, is being used to break the chemical bonds.
Not the chemical bonds.
The
Hydrogen bonds.
The hydrogen bonds, yeah, the bonds that holds the water molecules to the water molecules.
Right.
Now notice, folks, that it's starting to...
We are boiling. We boil at 92 here.
So yeah, we're at 92.6 degrees, 93, something like that. The water is going to just continue to boil. Now let's just see what happens to our curve here. And notice, folks, what's happening is the graph right here is flattening out. And what's going to happen is it's going to stay at the same temperature for a very, very long time. How long will it stay for that way, Mr. Sam?
Until all of that water's gone.
Which would be probably an hour from now, maybe a half hour.
Yeah, something like that.
Something like that. Notice how it's starting to flatten out.
Yeah.
Okay, so let's yeah.
Yeah, so we had a flat spot down at the bottom when the ice was turning into water because
Down
that was a
here.
phase change, very little temperature change, essentially no temperature change.
Yeah.
Then I jiggled the probe there, that's why that's all funky.
Yeah, that's weird.
And
No
then,
big deal.
whoops, sorry, I just took it out of the water.
Yeah, you can't take it out of the water, Mr. Sam.
Yeah, sorry about that. Then we have a flat spot on our graph again, and that's where the other phase change is occurring. So this is what we're going to call the heated up, break it up model here.
Okay, all right. Well, Mr. Sams, it looks like our curve is continuing to flat here after another 3 or 4 minutes.
We've let it boil a few more minutes, and it's still boiling, and it's still right about the same temperature.
Temperature still 95 degrees. It hasn't changed a whole lot. Probably it's resting on the bottom. It's probably whatever. Close enough, so it's going to continue to boil for as long as this right here is around until it runs out. And so it's going to be. We're not going to sit here forever and watch that, but it's going to last a long time.
Yeah.
Okay, so that is the heating curve of water. So what that really should have looked like, we saw that being made here in the lab, is it should really look like this.
Yeah.
So we started on the graph kind of right here, right?
Yeah.
And yeah. So
And we started with a fairly flat section.
Yeah.
And then we had a nice steady increase like you see in section C here. And then we had a flat section again, like section D. Now we never turned it all into steam, so we never really got up to E. But
yeah.
So we had B, C, and D on our graph.
All right. So what I want you to do is I want you to copy this this graph down in your notes. Make it nice and big. Take an entire page of paper.
Yeah, and
we're
if
going to
you're
label some things.
if you have
on
a printer
this.
hooked up to your computer, just
might-
hit pause and file print.
Yeah.
And you can print this out and tape it in there.
But we're going to add some things to this.
Right.
So what is true from here to here? This is water, of course.
Right. Well,
Is
it's
that-
frozen water.
It's
so
frozen
that's ice.
water. So
Yeah.
this is actually ice. So we'd say this is a solid.
Right.
So I'll put an S right there
Okay.
for it's a solid. So you're heating up a solid.
Okay.
Okay. So
And that's if we, stuck the thermometer in the freezer where our ice came from, it would probably be, minus 20 or whatever.
Yeah.
And then we could watch the temperature come up.
right. Now something strange happens in section B. What states of matter are present?
Well, we had solid and liquid present as we were melting the ice and when we had the flat part on our graph.
Good. So solid and liquid.
Okay.
And
Then we had the steady increase when it was just the liquid being heated.
So in section C, that's only the liquids, right? And in section D,
that's as it was going from a liquid to a gas. So both the liquid phase and the gas phase were present as we heated that up.
and if we were to somehow
as a
capture
boil, I
that
should say.
steam as it came out and were to heat it up
Even more,
separately,
yeah.
then this would just be a gas. So I want you to label these. So
Yeah.
here's the strange thing, ladies and gentlemen. The temperature does not change in section B.
Right, and section B is the melting
Yeah,
area.
so let's write this is melting.
And then section D,
Up here in section D.
temperature does not change, and that's the boiling section. So those are the phase changes. We get a flat spot.
So the energy is being used to break the bonds
Right.
that hold the chemicals together.
Right, so we're going to call this our heated up, break it up graph. Anytime the graph is going up, we are heating one phase. Anytime the graph is flat, we are breaking the bonds in a phase change. So we heat it up. When it goes up, we're breaking it up as it's flat.
Oh, so I got a question, Mr. Hams.
Okay.
Heated up. What section would be heated up sections? A, B, C, D, E. Tell
The
me.
heated up sections are A,
Yeah,
C,
I see that. C
and E.
and E.
Okay,
Ace.
A we're heating up the solid, C we're heating up the liquid, and E we're heating up the gas.
So, folks, you can see the temperatures rising. In the heated up sections, the temperature is going up.
Right.
Yeah. In the break it up sections,
Right,
what
that's
sections would that
sections
be?
B and D,
B and D.
and that's the melting and the boiling phases.
The melting and the boiling phases. So the energy is being used, but it's not being used to warm the temperature up. It's being used to break the bonds.
Break the bonds. Right.
Okay, good. All right, so that's important.
Okay.
So let's just talk about this. This is just another way to look at it. So how much, during a phase change, just a sort of an introductory question, how much does the temperature change when ice is melting?
It does
Mr.
not
Sims?
change.
No change? No change? You're adding
change.
energy and there's no
During
change?
a phase change, the energy goes to break the bonds, not to change the
Break
temperature.
it up. All right, so guys, here's kind of a good picture down here. If we can zoom in here, is we've got solids. They're all kind of together. Here's where it's freezing and melting in this first section, and the liquids are all kind of separated. And you see that? That's kind of a cool way to look at that. All right,
And now it's big.
now it's big. Okay, cool. What about vaporization-condensation? Well, there's
Okay.
another term, kind of like fusion and solidification. It's something called the heat of vaporization. The energy required to turn 1 mole of a substance from a liquid to a gas.
Okay. Now I'm guessing we're going to get a little delta H with a symbol. Oh,
Vape.
Vap.
V-A-P.
Yep, vaporization.
That makes sense. And its
Okay.
number is 40.7. Now, interesting enough,
that's a lot bigger than the 6 one.
Yeah, that's like 5 times more.
Yeah.
6, 7.
7.
7 times. So it's a lot more energy
You're good
to
at math.
boil water. Yeah, I had to think it through. So it takes a lot more energy to boil water than it does to melt ice
Yes, it does.
because the bonds are stronger. Okay. All right. And then we've also got the molar heat of condensation.
Right,
Now,
that's just going the
condensation-
other direction. That's going from a vapor to a liquid.
Yeah, gas to a liquid. Yeah. And this is called delta H cond. And guess what? The number's the same except
Different sign.
different sign.
Now this is an exothermic process, meaning as something condenses, it releases quite a bit of energy, which is actually why steam burns are really, really bad. If you've ever put your hand above a pot of boiling water and the steam hits your hand, it hits your hand and it feels really hot. And it's not hot just because it's the temperature, but
Yeah.
as it condenses on your hand, all that energy gets
Yeah.
released into your hand. So steam burns are pretty nasty.
They're worse than just a regular hot or boil.
Yeah.
Yeah. So here's kind of we go back to our graph here. You don't have to recopy this, but I want you to notice right here. This number here is 6. That's 6 kilojoules, right? And this was 40. That's a 4. Okay,
That's why-
42 or whatever. But this number is this graph part here is long because it takes more energy to boil the water than it does to melt that same ice,
Yep.
same mass of ice. Okay. Now let's talk lastly here about how that relates to something called kinetic energy.
Okay.
So how could we label this graph for kinetic energy? All right, now when we talk about something called kinetic and potential energy, let's talk about kinetic energy, Mr.
Okay.
Sams. What is kinetic,
Kinetic
energy in
is-
this context?
Well, kinetic energy is energy of motion, and when molecules are moving around, that's really how we get temperature. Temperature is based on the average kinetic energy.
And actually, folks, there's actually an equation. Let's go ahead and copy it down.
All right.
Kinetic energy is 3/2 times R times T. We'll learn later on what R is, but T is temperature. So that means that the higher the temperature, the higher the kinetic energy.
Right, so all the places on that graph where our temperature is going up, kinetic energy is also going up.
So in part C, here, kinetic energy is going up right here. And that would be true in A, right? Section A, and also true Section E, by the way, just keep going like that. And so we would say kinetic energy is going up. But, you know, in sections B and D,
the kinetic energy
we
does not change.
are not changing the kinetic energy,
Right.
but there is more energy.
Right,
going
we're putting energy in, so we're actually increasing the amount of potential energy.
All right,
in there.
so the potential energy goes up in section D and also in section B. Again, what you ought to do, guys, is copy these down and recopy, you know, put this on your graph. So there's a difference. Now, what is the difference between potential and kinetic energy?
Kinetic is energy of motion.
Yeah,
Potential energy is stored up energy.
Yeah, so we should maybe define potential energy. Potential energy is stored energy. And think of a candy bar, guys. A candy bar has, or a Cheeto.
Yes.
That Cheeto, that nasty
Orange, glowing goodness.
That Cheeto has energy in it.
In its chemical bonds.
In its chemical bonds. It's stored, so it is considered potential energy. Okay, so hopefully that helps you understand conceptually how all this works.